Welcome to Maths with EJD. In this video, I'll be talking about the mixed strategy Nash equilibrium in the rock, paper, scissors game. Um, let's see the overview of the rock, paper, scissors game. What does it look like? First of all, in the game of rock, paper, scissors, going forward, I'll just refer to it as RPS. Okay. In the game of rock, paper, scissors, players simultaneously choose one of three actions. One of three actions. So that's more like their strategies, right? And the actions are either rock, paper, or scissors. I mean, you do the motion with your hand. Rock is something like when you make a fist, when you turn your hand into a fist. Paper is like when you open your hand, and scissors is like when you use your two fingers to make a scissors. So that's the idea. So it's not like you actually use an actual rock, paper, or scissors, but you use your hand for these demonstrations. So now the thing here is that each action, each action beats one action, beats one action, loses to another, loses to another, and ties with itself, and ties with itself. So that simply means that if two people are playing the game, I mean, as many people as possible can play the game. So, but if two people are playing the game, right? And for instance, if I end up with a rock and the other person ends up with a paper, then the paper person wins me. If I make my hand into a paper and the other person makes his hand or her hand into a scissors, then scissors wins paper. So basically, scissors wins paper, paper wins rock, something like that. And then I think rock wins scissors. I'm not sure which one now, but of course, when we see the payoff matrix, you'll understand which one wins. But if both of us show rock, then that's a tie, and that'll be 0 point for each of us. So each action beats one action, loses to another, and ties with itself. So in essence, paper loses to scissors, but paper wins rock. Then scissors wins paper, but loses to rock. Then I think rock loses to scissors, but then wins paper or something like that. But I mean, the payoff matrix is going to show us what exactly the situation is. So each action beats one action, loses to another, and ties with itself. Okay, so a mixed a mixed strategy. Okay, let me make that in capitals because that's like a big thing, key thing here. A mixed strategy Nash equilibrium. A mixed strategy Nash equilibrium occurs when players randomize their choices. So, I mean, randomization of choices is such that nobody can guess what you're going to come up with. So when you're playing, nobody knows if you're going to end up with a paper or rock or scissors. So when players randomize their choices, okay, in such a way that no player can improve their expected payoff by unilaterally changing their strategy. in the previous video, I actually listed if the steps we need to follow to reach mixed strategy Nash equilibrium. So, a mixed strategy Nash equilibrium occurs when players randomize their choices in such a way that no player can improve their expected payoff by unilaterally changing their strategy. Okay. All right. For the rock, paper, scissors game, let's see the payoff matrix. Payoff matrix. So, as usual, I like to do it this way. So, we have player one, player one. So, player one's things are here. And then we have player two. So, for player two, we have the actions of the payoff. I mean, the actions player two will take are down there. Mm, okay, player one, player two, player one, player two. Okay, let's do this way. Player one will be it's let's reverse it. Okay, player two here, player one here. So this is player one and this is player two. Okay, so imagine this is rock for player one, paper for player one, and scissors for player two. Then again, you have rock for player two, paper for player two, and scissors for player two. Okay. All right. So now see what happens if player one and player two, if player one and player two both do, player one goes rock and player two also goes rock. So that will be a tie. So both of them will have the payoff for both of them will be zero. But then if player one has goes rock and player two goes paper, player one loses and player one gains. Player one loses a point and player two gains 1 point. Okay, because paper dominates rock. Paper is a better strategy than rock, so to speak. All right. Then if player one goes rock and player two goes scissors, uh, you know, rock wins over scissors. So player one gets one and player two loses a point. Okay. And when we come down, if player one goes paper and player two goes rock, player one gets a point because paper wins over rock, and player two gets -1 point. Okay. Now, if both of them go paper paper, that'll be a tie, and they both get zero. Then, if player one goes paper and player two goes scissors, paper paper loses to scissors. Scissors wins over paper. So player one gets loses a point and player two gets 1 point. Then just like we know scissors and rock, for scissors and rock, uh scissors loses to rock. So player one goes -1 and player two gets one. Okay. Then if you have scissors and paper, scissors wins paper. Okay. So player one gets 1 point, player two gets -1 point. This is a zero-sum game. That's why if you add the 2 points, you will end up getting zero. Then if they go scissors, scissors, you have 0-0. So that would be the payoff for a rock, paper, scissors game. Now, the next thing we want to talk about will be to find the mixed strategy Nash equilibrium. Okay, so let's talk about finding mixed strategy Nash equilibrium. Okay, so here we say let P, Q, and R represent player one's probabilities, player one's probabilities of choosing rock, paper, and scissors. Okay, respectively. Similarly, let P prime, Q prime, and R prime be player two's probabilities. Okay, so now we have number one. Let's look at player one's expected payoff. Okay, so here, player one's expected payoff for choosing each action. That would depend, right? It's a game. So player one's expected payoff for choosing each action depends on player two's mixed strategy. Player two's mixed strategy. Okay. So now, as you can see, right, this is all these ones are for player two. Player two, all these are for player two. So if that is the case now, if we go for rock, player one's expected payoff for choosing each action depends on player two's mixed strategy. So if you now say for rock now, for rock, what happens? You have U of R. That is the expected payoff for R will now be, so for rock, so that'll be 0. So of course, talking about player two, for rock, this is rock for player two now, this whole thing. This is rock for player two. So in that case, we have 0. In that case, we have 0 minus 1, 1 for player two. Okay? Because that is going to determine what happens to player one. Then when we go comp of paper, so for rock, 0 minus 1, 1. So that, and with that now, we have this expression that that is 0 p prime, okay, minus 1 q prime. That is the probability. We already know p prime, q prime, and r prime are the probabilities for player two. So the probability of picking rock, I mean, the payoff for picking rock here is 0, and the probability of that is p prime. The payoff for picking rock when player one picks paper is -1, and the probability is q prime. And then the payoff for picking rock when player one picks scissors is actually 1. So in that case, we have 1 multiplied by r prime, okay, for player two. So this is player one's payoff, depending on what happens to player two. Okay, so we have this. So this can be tidied up as minus q prime plus r prime. Okay, can be tidied up that way. Then that is for rock, right? For player one. So if you now go for scissors for player one, scissors for player one. I mean, sorry, if we go for paper for player two, rather, whatever happens to the payoff for player one depends on what player two does. So if player two chooses paper, let's look at all the possibilities, So here, it means you're going to have, okay, that's be 1, 0, 1. So, if player two chooses paper and player one chooses rock, the payoff is 1. The probability is P prime, right? Paper two, if player one chooses paper and player two chooses paper, the payoff is 0. If player one chooses scissors and player two chooses paper, the payoff is -1. So we have 1, 0, -1 again. 1, 0, -1. So now we say paper, for paper, we have U of P, and that is again 1 P prime plus 0 Q prime minus 1 R prime. That is simply the same thing as P prime minus, that's P prime minus R prime, okay? P prime minus R prime. So for scissors also, for scissors, that's scissors for uh, player two now. So for scissors for player two, we have this whole place. Okay. So, and then we'll be focusing on that was -1, 1, 0, -1, 1, 0, like that. So that for scissors now, for scissors, the expected playoff focusing on scissors would actually be equal to um that's -1, 1, 0, -1, 1, 0. That'll be -1 P prime plus 1 Q prime minus 1 R prime. Okay, is that it thing? -1, 1, 0. Sorry, this is -1, 1, 0. So -1, 1, 0. So this will be 0 R prime, meaning we have minus P prime plus Q prime for scissors now. So one thing that must be understood is that in equilibrium, we are talking about, we're looking for the mixed strategy equilibrium. So in equilibrium, okay, player one must be indifferent. Player one must be indifferent. In equilibrium, it means whatever player one does, whatever player two does, player one doesn't care, right? So in equilibrium, player one must be indifferent among all actions. So whatever player two does doesn't bother player one when at equilibrium, because at equilibrium we are going for the strategy that cannot be affected in any way. So in equilibrium, player one must be indifferent among all actions. Thus, so the implication of this is simply that U of R is equal to U of P, and that is equal to U of S. Okay. So in that case, we can equate. So it means that all these expressions, this is equal to this is equal to this. That is what that simply means. So we can actually equate them and solve them. But before we, because whatever is happening there is exactly what is going to happen with player two's payoff, depending on player one's activities. So let's look at player two's expected payoff. So exactly the same thing. So here now we say similarly, player two's expected payoffs for choosing rock, paper, and scissors depend on player one's mixed strategy. And don't forget the probabilities for player one choosing rock, paper, scissors PQ, and R. So here now we say for rock. So now for rock, see what happens. Let's go back to the table. For rock now, for player 1. So let me erase all this. Okay. For rock for player 1, this is where we now focus on. So for rock for player 1, we have 0 minus 1 1. Okay. 0 minus 1 1. In that case, that means that we have 0. That'll be 0p plus 0 minus 1 1, right? So that 0p minus 1q plus then plus 1r. Okay. 0 minus 1 1. And that is simply equal to p. Sorry, that will be simply equal to minus q plus r. Okay. Minus q plus r, because of course this is 0, right? So that's minus q plus r. So that's for rock. For paper, so for paper, let's go back to the payoff table. So for paper now, see what happens here. So this is gone. So for paper, we now have this for player 1. And so for paper, right, when player 1 chooses paper and player 2 chooses rock, so we have 1, 0, minus 1, 1, 0, minus 1. So we can go back and do 1, 0, minus 1. So here we have 1p plus 0q minus 1r, and that is p minus r. Okay. Then finally for scissors now. Okay, for scissors, so because player two's action is determined by what happens to player 1, so we focus on player 1's expected payoffs. So here, when player 1 goes scissors, okay, and player 2 goes rock, the expected payoff for player 1 is minus 1 1 0. So minus 1 1 0. So we can go back and do minus 1 1 0. So this is minus 1p minus 1p plus 1q plus 0r, and all of that is minus p plus q. And just like in the case of player 2, right? In equilibrium, player 2 must also be indifferent. In equilibrium, player 2 doesn't care what player 1 is doing, because in equilibrium, player 2 is going for the best option, whatever player 1 does. Okay. So in equilibrium, player 2 must also be indifferent among all actions. Indifferent among all actions. Okay. One thing I forgot to do is, I did U of R, U of P, and U of S. But here this is like U of R prime, because, we are focusing on the expected payoff for player 2. So U of P prime, and then this is U of S prime. Okay. I should have written that previously. So in that case now, since player 2 must also be indifferent among all actions, it simply means that U of R prime is equal to U of P prime is equal to U of S prime, meaning that this is equal to this is equal to this. That is going to help us at the next stage of this whole thing. So let's now go to solving for the mixed strategy now. So we want to get those probabilities P, Q, and R. Solving for the mixed strategy. Okay. So that simply means that we are going to have so we are assuming symmetry, right? As we've seen already. So assuming assuming symmetry of strategies. So if you assume symmetry of strategies, okay, because all the same strategies are available to both players. So that simply means that probability P is equal to P prime, probability Q is equal to Q prime, and probability R is also equal to R prime. Okay, so nobody has an undue advantage over the other person. So in that case, now we now go ahead to talk about the indifference conditions. So for indifference conditions, okay, should I list that? Okay, so here, next thing is we now talk about the indifference condition. So for indifference, right, you have already said that all the expected payoffs are equal for each player. So this, and since you have taken, so either anyhow you go. So if you take like U of rock, expected payoff for rock is equal to expected payoff for for paper and expected payoff for scissors. You can do that, or you say R prime equals U of P prime equals U of S prime. Anyhow you go, you can do that. So we can now revisit. We see U of R prime is minus Q plus R. So this simply tells us that minus Q plus R is equal to U of P prime. That is, you can choose anyone. You can even choose the one for player one up there. So P minus R is another one. So we have P minus R. And lastly, we have this is not minus, this is equal to. And lastly, we have minus P plus Q. This is minus P plus Q. So minus P plus Q. So what we want to do now is we want to solve for P, Q, and R. We already know P and P, Q, R will also be equal to P prime, Q prime, R prime, respectively. So this is exactly what we have now. This is what we have to deal with now. So if you can solve from this using and we know there are probabilities, don't forget. So because those two information are really going to help us. So if we start with this now and say that, okay, since minus Q plus R is equal to P minus R, what does that mean? That simply means that R plus R, if you bring this R here, so you have R plus R is equal to P plus Q. So that simply means that 2R is equal to P plus Q, right? So meaning that R is equal to P plus Q all over 2. So we can hold this as equation, call it equation 1 if you like, or call it whatever is convenient. So we have R equals P plus Q equals 2. So that's one way. So we can hold that. We can't go further with that. Now let's go on. We can now say, okay, so for the first one, right, we had actually said this is equal to this. What if we now pick the next one and say Q plus minus Q plus R is equal to minus P plus Q? Okay. So that means also minus Q plus R, all right, is equal to minus Q plus R is equal to minus P plus Q equals minus P plus Q. Now, what that simply means is that we have R plus P, because this can come. R plus P equals, this can go. R plus P equals Q plus Q. So that means that R plus P is equal to 2Q. Okay? So that means 2Q is equal to P plus R. Don't forget, from here we already have R. Okay? So let me just leave this and label it as equation 2. So let's say this is equation 2. So we can now substitute. So we can substitute equation 1 into equation 2. So substitute in equation 1, right? We have R. R equals P plus Q over 2 in equation 1. In equation 1 into equation 2. Into equation 2. So that simply means that 2P equals okay. Sorry, this is 2Q. Sorry. This is 2Q. 2Q equals P plus R. So this is 2Q. So it's 2Q equals P plus R. So this can go. This is 2Q equals P plus R. So, and we are bringing this, we are replacing this P plus Q over 2 for R. So we have 2Q equals P plus, instead of R now we have P plus Q over 2. So we can multiply through by 2. So that means 2 times 2Q is equal to 2 times P. The reason for multiplying is because we want to remove the 2 down there. So P plus Q all over 2 times 2. Okay. So that uh, this cancels this. And we now have 4Q equals 2P plus P. That thing is plus, right? This is plus actually. So this is plus. This is plus. Okay. So this is 2P. So 2P equals P plus Q here. So we have 4Q equals 3. Okay. I mean, from there, right, we can now transfer a Q. So we have 4Q minus Q because this Q can go here, and this is equal to 2P plus P. Okay, so this is 3Q equals 3P. Interestingly, 3 cancels out. That means that P is equal to Q. Okay, so P is equal to Q. That is one result we get. So it means P and Q are exactly the same. Now, on the other hand, we still have one pair we have not taken. Can we take the last pair? This is P minus R equals minus P plus Q. P minus R equals minus P plus Q. All right. So we say again, P, what's that thing again? P uh P minus R equals minus P plus Q. P minus R equals minus P plus Q. So that means that P plus P, that is if this comes. So P plus P equals Q plus R because minus R can become plus R here. So we have 2P again equals Q plus R. But interestingly, we already know that P is equal to Q. Okay? P is equal to Q. Okay, I guess we can call this equation 3, right? So we can call this equation 3. So so we can now say since P is equal to Q, so basically we can then have um so 2P plus, 2P equals Q plus R simply implies that 2P is equal to, see, P is Q, so it means Q now can be P, and this is equal to R. So we have 2P minus P equals R. So that means that 2P minus P is equal to R. So we already know that, okay, so we already know, I guess I want to also call this equation, this should be the fourth equation, right? This is equation 4. This is equation 4. So in equation 3, we know P is equal to Q. In equation 4, we know P is equal to R. So we can combine both. All right. We can combine both. Combining equations 3 and 4. If you combine equations 3 and 4, equation 3 tells us that P is equal to Q. So P is equal to Q and P is equal to R. Okay. So you see, P is equal to Q and P is equal to R. So it's the same P. So it simply implies that P is equal to Q, and then if P is equal to Q and P is also equal to R, that means that P is equal to Q is equal to R. So all the values are the same. But since P, Q, and R are probabilities, okay, and we know that when we add probabilities together, PQ plus R will simply be they must add up to 1. But since they are all equal, so since P equals Q equals R, so we can simply say that uh, we have P plus P plus P is equal to 1 because they're all equal. And then we have 3P equals 1. And we can divide through by 3. So 3P over 3 is equal to 1 over 3. So this cancels out. So P is equal to 1 over 3. All right. So this is a very important result. But since P, Q, and R are all the same, we can now say, therefore, P is equal to Q is equal to R is equal to 1 over 3. So that is what we end up getting. So those are the probabilities, that we have. So in this case now, so the indifference condition has led us up to all these points. And don't forget, it means that the probabilities of rock, paper, scissors for either player, because we have already also agreed. So, I mean, if this PQR is 1 over 3, that means that P prime is equal to Q prime is also equal to R prime is equal to 1 over 3. All right. So having done that condition thing now, so we can now go for 2 and we talk about the verification. Verification. Okay. Um, so the verification is simply now about the fact that the so this probability now makes everything unpredictable. So we now say at P equals Q equals R equals 1 over 3 equals 1 over 3. Neither player can improve their expected payoff by deviating unilaterally. Okay, by deviating unilaterally. Okay, so that is what we get now. So we can now in conclusion, right? In conclusion, we have that the mixed strategy Nash equilibrium, all right? The mixed strategy Nash equilibrium, okay, for rock, paper, scissors is for both players, to choose rock, paper, and scissors with equal with equal probabilities. That is 1 over 3, 1 over 3, 1 over 3. And what this does is that this ensures no predictable pattern. This ensures no predictable pattern that can be exploited. By the opponent. So that actually makes rock, paper, scissors a very fair game because you never can tell what your opponent is going to do because there are equal probabilities of choosing rock or paper or scissors. So, I mean, that's been an interesting one up till now. So, you want to go over that and really get used to it. So, in the next video, I'll also be talking about the mixed strategy Nash equilibrium in the matching pennies game. So, where you have head and tail matching and things like that. So, watch out for that. And you want to subscribe to the channel so you don't miss out on anything going forward. So, subscribe to the channel, hit the notification bell so you can always get alerted each time a new video is released. And then comment, let me know if you want me to teach a topic or solve a problem, and like and share so that more people can have access to this great content. Till I come your way again, keep playing the game of life with wisdom. Bye.